Is this clear? Can you hear me? No? This better? Yes. This is people saying yes. Okay. Yes, as the introduction said, I'm going to talk about security in PDAs, and specifically the PDA with the DSM phone built-in. From our point of perspective, it's the most interesting device because it is really getting connected. With GPRS, you get internet wherever you are. And yes, what I want to do is show you what we've been playing with the last year, and what you can do with such a device. Yes, as a hacker. So in that sense, I'll also be looking at a little bit more at the device from a hacker's perspective instead of security perspective. I consider the security issues mostly appear almost from itself once you start understanding how a device works. So understanding is a prerequisite to do proper security research. Okay, so I want to go along this talk along all kinds of topics, and it's a bit of a mix of all kinds of stuff. I found out in the end that I had something like 60 slides, so it's a bit much maybe. So for some parts maybe I'll skip a bit too quickly. If you have some questions on issues you want to have some more background on, you can just ask me during the presentation, and I'll be around also today and tomorrow, so if you come up to me and we can discuss anything you want to. Maybe also more on the security aspects that maybe result of what I'm showing today. So what I first want to do is a quick motivation of why hacking devices, why this device, what are the devices out there. Then show you a little bit of background into what is a Pocket PC device, what is specific about Pocket PC. Then I want to go into the hardware. So what does it look like? How do you find out what the hardware is doing in an embedded device? Then go on to hacking the software that's in it, and show you a little bit on the tools that you can use to discover what's in the device, but also some tools that have been built to do the tricks that we do. So the motivation for playing with these devices. Well, first of all, I don't think it needs an explanation to tell you that a PDA is a interesting device from also the security perspective. The things that we will be doing in the future, especially with PDAs, the data that will be stored on there, the connectivity that it will have, initiated by you as choice, but also initiated by the device without you knowing it, maybe. The wireless aspect is very difficult to understand and see aspect of the security. Also, the fact that actually hacking these devices doesn't get that much mainstream attention. A few years ago, I found an SMS bug that you could crash a Nokia phone with, and that was in the news shortly. But for the rest, you don't see that many actual problems in these devices occur in the media. And thirdly, I think hardware hacking, so understanding the hardware as opposed to only the software, will become more and more part of the security research that we will need to really determine if devices are secure or not. So, what can you hack? Well, a few years ago I got a 6010 Nokia, so I took it apart. Then I got an XDA, which is like the first generation DSM Pocket PC phone. I took it apart and we played with it. And 2 weeks ago I got this device, and I haven't played it with it that much yet, but it's the new XDA2, which is more powerful, has more connectivity, it has Bluetooth among other things. But they are all phones, so that's an important aspect of them. Okay, so what is a Pocket PC Phone Edition? Pocket PC is an OS, so it's an operating system, and as operating systems go for PDAs, there are mainly 3 of them at the moment. You have Palm OS, which has been around the longest. Then we have Symbian, which is a predecessor, it's coming after or based on Epoch, which is, I think, the Optime OS. And then there's Microsoft with its Pocket PC Windows CE version. So we are today only talking about a Pocket PC, so I've never looked yet at Symbian, for instance. Okay, what is Windows CE? Windows CE is an operating system developed by Microsoft based on its knowledge of Windows itself, but specifically targeted at embedded devices. So it's not a port of Windows for the desktop to an embedded device. It's a complete from-scratch implementation of a new OS. Of course, they use a lot of the features and APIs and whatever from the normal Windows, but it's a new implementation. And that means that also a lot of things don't work as you would expect from the desktop. Also, Windows CE, so not Pocket PC, but Windows CE, which is the core on which Pocket PC is based, the core is meant for a broader range of embedded devices. So it's not only meant for PDAs, but it's meant for embedded tools everywhere. So you have embedded hand scanners and I don't know what for industry use, automotive, like onboard computers for your car, smartphones, of course, which is very close to Pocket PC. But actually, they are all derivatives or modifications on top of the Windows CE. And specifically for these devices is that, of course, they are tuned to very much the footprint of a normal embedded device, which means there's not that much RAM, or there's no hard disk, or mostly you use flash ROM for it, and that has special requirements for how you do the memory management, etc. Flash file systems, things like that. Okay, so what have we seen for the Pocket PC Phone Edition? Well, the main implementations have been done by a Taiwanese company called HTC High Tech Computing, and they were the original manufacturers of the first iPads. So HP had HTC make the iPads in the first few generations. HTC then moved on to putting GSM parts into these PDAs, and they were first sold as the XDA4, and this is because they are branded by several companies like T-Mobile, MDA, etc., etc. And currently with the XDA2, this went even further, because originally there were only a few, but now I think the XDA2 is branded as well, maybe 10 different brands. And what's in there, we'll get back to in a bit. Okay, so, well, this is a bit dated, but so the smartphone is one of the other developments. So this is a different form factor, less memory, less UI, really meant for a phone, while the XDA is really meant as a PDA. So it's much more like a small computer than the phone is. Okay, so once you get such a device and you're interested in how it actually works, the first question is, okay, what's in it? You want to know what's in the device. So what you do is you open it up. That's the only way to figure out what's doing in such a device. This is actually a picture from the FCC. The FCC is the organization that certifies equipment for radiation purposes in the US. And before you can sell something there, you need to be certified, and they do research. And as part of that research, there are all kinds of documents that they publish. So if you go to the website, you can see products that are not on the market yet, and they have documents for them. And part of them are photos, for instance, of the internals. Slowly, the manufacturers are figuring out that they don't want to put so much public information into this tests for the FCC, so they now have the option to remove all kinds of data from it. But especially for this one, they still put in quite a bit of info. So the next step is, if you have a board and you get it out, it's okay, you look at the board and you try to figure out what the components are. On the components there are numbers, there are manufacturer names, and you just start mapping basically what's on the PCB. Not that you're going to see from a PCB anymore how it's connected, because that's in all the layers below, so there's no point in really seeing how the function works. On the other hand, the design is always split in areas that are grouped together, and you can sometimes see it from the shielding plates that group certain areas. In this case, well, the CPU is clearly visible. In this case, it was strong arm. The memory, Winbond, well, very well-known memory manufacturer for the SD-RAM. Less known, the TI part that was on there. We could only find a few hints of what it was doing, and now that we are a year further, we know that TI is branding a whole chipset for GSM wireless, and it's called OMAP, and this is probably a predecessor. But you can find the types with Google and with search engines. You can really find quite a bit of info on the background of these devices. So this already gives you an idea of, okay, what components are there, and if you later go into the software, you already have an idea of what you are going to expect to find there. Or use, of course, the documents, because in this case, they had a full block diagram of the device on the website, as you see. So even before we had to look at the board, we already knew more or less what was going to be in there. And what you can see here is that such a phone device in the PDA actually has two processors. So you have the strong arm running the Pocket PC OS, but there's another processor combo called the DSP ARM combo, which is actually running the DSM phone. So there are two processors in there, and they're functioning completely separate. So the phone can be on even while the mobile, while the Pocket PC is rebooting. The phone can keep on running. Of course, you can't do anything with it because for the keypad and you need interfaces with the Pocket PC. But it's pretty separate. So the next step for finding out what a device is doing, you need aids to get into the hardware and find out what the hardware is doing more and more. There are more and more custom components. If you look at the board like I showed, there will be several components with numbers that don't mean anything to you, that you won't find anywhere on the internet, because they are ASICs developed by HTC themselves. And ASICs are logic blocks that are used for extending the I/O, mostly for chips, or for putting in simple logic, for instance, to drive certain buses, for the SD bus, or for anything that the main processor doesn't support initially. So one of the components, however, that's part in almost every logic device these days is called JTAG. And JTAG is a protocol or a definition for something called boundary scan. And what it does is, if you see the block on the right, a chip has all kinds of pins that they are using for I/O. The data bus, the address bus, GPIO for controlling digital I/O lines for sensing buttons and stuff like that. And what JTAG does is it places a cell for every pin on the device. And through another set of pins, it lets you control these cells. So on the left-hand bottom side of the block, you see three lines called, or actually, those are the state, the clock, and the reset line. And then you see TDI and TDO, which is the input and the output line. And by using a serial protocol, you just use it as a shift register. So from the TDIO line, bits are shifted in, and they go through the cells and out the TDO port. Now, what you can shift in are bits, of course, so you can shift in a 0 or a 1. And depending on the state of the cell, you can use them to set or read the cells, the pins of the device. So through a very simple serial protocol, which is only taking 5 lines, and actually for the protocol itself only 3, because you have the data in, the data out, and a clock. can modify and monitor all the pins of the device in circuit while the device is running. So the device can be running, the Pocket PC OS, whatever, and you have constant control over all the pins of the device. So this is a very powerful mechanism, and it was first developed for in-circuit testing. So the idea was, if you have such a component and you have a second component, because you can just daisy chain them, you can just put another TDI line on the TDO of this one, and they just add to the shift register. So your shift register for your PCB just gets longer, and you can address the different chips on your board. And the first idea was, if I put a 1 on an output pin, and then on the device that should be connected, I read the pin there, I can see if the PCB trace is working or not. And in this case, I could test if the PCB was fully functional. I could test all the pins and all the traces on the board and see if there were connections where there should be, or I could even see where there were shortcuts, stuff like that. So it wasn't to do with the device itself at all. It was just meant for testing traces on the PCB as a first step. But of course, it's much more powerful. So these days, pretty much every CPU is supported. So also the Intel CPU in your PC, chip, CPU chip, whatever, everything is supported with JTAG because it's so useful. The only thing, of course, is if you have a hardware device that you buy, how do you find those 3 or 5 lines? And that's a difficult part because they are not going to tell you. So for this case, for the XDA, what I did was this. I put it in the oven. Why did I put it in the oven? If you look at the manufacturing process of the PCB, it's using SMD components. So that means that there are only tiny, tiny, tiny pins, or if it's a ball grid array chip, there aren't any pins. There are just droplets of solder on the bottom of the chip that's connected to the board. So there's no way you're going to get to the pins of the device anymore in the modern manufacturing of these PDAs. So the only way is to get them from the board. Now, if you look at the manufacturing process, they are put on the board with hot air. So they put them on with air of about 200 degrees, and they're soldered like that. So one way to desolder them without any expensive equipment is to take an oven and just put it at 200 degrees. And then when the board is hot, you just lift off all the components that you want to remove. Of course, the manufacturing process specifies that you can heat a component generally for about 10 seconds at that temperature. And if you use this method, you won't do it in 10 seconds. So that means that all your components will be gone. Luckily, I had someone that sent me a broken XDA, so I could do this on. And I also haven't done it yet with my XDA too. So, but it's a fun experiment, and also it worked very, very well. It was very easy to lift just the components that I wanted to remove. It doesn't go floating off the board all at once. This is the result. So maybe you remember with the board with all the circles. Well, there are quite a few components gone now. And using this board, I was able to trace. I'll walk to it. So this is where the CPU was. So this is a 256 pin VGA. That's split here, 16 pins of 16. And what you also have on a board like this are these copper pads, which are the test pads that they are using in the manufacturing process or in the repair process to see what's going on in the board. And in this case, what I was gambling on is that a few of those test pads would be used for the JTAG protocol. And tracing this, I found quite a few. So these 2 pads were used for it. That here was used for it. On the other side of the board, a few pads were used for it. And you just use an resistor meter to find the connections and see where the pins that you want to see are going. So that resulted in the locations I just mentioned. You just connect the wires to it, and that gives you JTAG access to your device. So what can you do with JTAG these days? Well, one of the few simple things is you can, as the machine is running, you can read all the memory. And you don't need to write a program and put software on the device to do it. You can just use the 5 wires and read all the memory as it goes. So that's an interesting thing to monitor a device if it's really closed. Of course, with an XDA where you can write all your software you want and put it on, it's not really necessary to go through all this trouble to read memory in this way. But in the future, when systems will be more closed, it might be an interesting endpoint. But you can also modify memory. One of the things JTAG now is used a lot for is, of course, for flashing in bootloaders in devices that have not been personalized yet. So if you have a device that can't run software yet, how are you going to get the bootloader in there? Now, one of the possible ways to do that is using JTAG. So if you look at the IPAC Linux support groups, etc., they are often using JTAG to put the flash code into the device for booting. Also, what's supported is debugging. Now, this is an area where you get into proprietary extensions for manufacturers. So a lot of this code doesn't always work with the normal open software that's available. But it is possible to do in-circuit debugging, which means setting breakpoints, stopping the code wherever you want, sampling code, setting watch points, stuff like that. And that's both supported by Intel, only you have to buy their software to do it, or by ARM, the ARM manufacturer, the licensor of ARM itself, with the ARM icebreaker. So already we see that JTAG is already seen as a security issue for the manufacturers themselves. So if you maybe have heard of the Xbox hacking that happened by Bunny, he hacked basically the Xbox and tried to circumvent the security mechanisms in it. And one thing that he saw is that the JTAG pad there had been removed. So the test pad on the board you could clearly see it had been there, but it was no longer connected to the plane in the middle of the PCB. So getting it connected was quite a trick there if you wanted to use that. So he didn't use that in the end. Also, it's known that there are fuses in CPUs that they can blow so that the JTAG stuff doesn't work anymore. There's also some open source software available to play with JTAG, and it's actively developed, and it's getting quite useful. I've got a little demo here of what you can see and do with JTAG on an XDA that I brought with me. So I'm now going to switch and see if it all keeps working. That still works. Okay, so, well, I had one problem, and that was that I thought it would be wise to put the latest software here on my system. And of course, with the latest software, it didn't work anymore. So I tried to get it back to work. I'm not sure how much will work, so I can't show all the things that I wanted to show. But the basic thing is quite simple. I've got a parallel cable connected to the laptop and a small board, which is a very simple level converter, basically. So the software is derived from the parallel port, and the pins are used to do the clock and the data in, data out. And this is the PDA where I have the 5 wires connected internally. Okay, so if I give a detect, it gives an error now, just because it's not properly turned on. Because if you remember, one of the 5 lines is a reset line, and it needs to be pulled low before you start the device, and that way it knows that JTAG is being used. So now I turn it on, and then we're you see is I'll move it up a bit maybe, is that it immediately recognizes the device as a strong arm. It's booting the Windows C now. Let me see if it still works, because this is what I meant. Yeah, okay, now it's working again. So, what's the case is that every device has a special code internally. It has a manufacturer code and a device code, and they are unique, so you can identify devices on your board. And in this case, the chain is only one device long, so the only device in the chain is the strong arm itself. But actually this could be a whole list. So if you have several CPUs, they could put them in a chain. For instance, the GSM part, they could have put them in the same chain, and then you would have seen both. And then you can, through the software, say which device you want to execute the command for. So this is an older version of the software. Actually, the command list is longer, but if we look at the commands, then there are several, like discovery. It can try and discover if there are more systems on the chain, or if there are unknown systems on the chain. Because to really use the device, you have to know how many pins are on the device. There's no way to query the strong arm and let it tell you, oh, I'm a device and I have 200 pins. So you need the proper configuration data already with your program to be able to use it properly with the device. So it's also no use for a component that you don't know that much about. Well, no use is a big word, but it's less use. It's very useful for devices that are known and where the whole list of pins is known. Well, one of the things that you can do with this is use the command read memory. And for instance, well, I know that there's an interesting area in the beginning. So if we say we read about this much data to say a file xt9, it's now reading over the parallel port. Okay, it's done. So now we switch to the other window. And if we do a hex dump here, then you can see here some code, and in the right column you can see some data that comes from the bootloader in the device. So you can just read out all the memory now, even if the device and hardware, for instance in the software, security will be built in that you couldn't read this, which in theory is possible. You could write software that limits your applications in reading these areas, for instance. Now this isn't the case for the XDA, so you can read this data from the XDA itself also. But for some devices it might be an option to actually read memory areas where normally you wouldn't have access to. Okay, so, well, basically, yeah, there were some things I wanted to show with, you could, for instance, there's the get signal of device 0, and then I can say, okay, I want to see what's on GPIO pin 4. So in this case, okay, the value is 0. So you can, in this sense, yeah, read and set GPIO pins while the device is running its software, and that way you can also find out what they're used for. You set one on 0 and then the display goes off, you know it's related. Okay, so far for the jetting stuff. So now we move back to my other PC. Okay, so like I said, this is what we found for the XDA1. The strong arm and a Hercom chip. Okay, the Windows CE. Well, like I said, it's very similar to what the iPad was doing. So in that sense, it's like a normal Pocket PC stack. All the iPads also had a bootloader that you can trigger by pressing a combination of the power button with a reset button. And we'll get back to what you can do with the bootloader in a bit. And what we found is the two parts. So the Pocket PC and the GSM are actually talking to each other over a serial line. So that's the only communication almost that they have. Might be that they have one or two GPIO lines, but most of it is happening over a serial line. So it's not the case that the Pocket PC is extended with some GSM stack software or whatever. It's pretty basic AT commands. And this is some other info that we just got from the TI website. Information about the components. So if you looked up the chip number from the board and you go to the website, you find block diagrams and you can find information on what the software is doing. It's not very detailed, but you can find some info. Okay, so that was what the hardware was doing. Now what the software is doing. And one of the most interesting parts of the device is the bootloader. And a bootloader is a component that basically starts up the device as soon as power is supplied. It has also a role in suspending, so if you put it to sleep. But next to the basic task of just booting up the Windows part of it, it's also often used for all kinds of other stuff, like initialization in the case of software upgrade or diagnostics, or other features that people don't want to have in the main OS, but in a case that the main OS crashes or is broken, that you have like this backup possibility to get some data into the device or information out of the device. Because all these functionalities are running in a completely different environment. I mean, it's running while the Pocket PC is no longer running. It's just replacing the Pocket PC OS. And because of that, it actually has quite a lot of security impacts. Because the memory for the Pocket PC is still live in the device at the moment that the bootloader is running. So if you can read memory from the device in bootloader mode, it's not subject to any controls or restrictions from Pocket PC because that's not running at the time. And vice versa, you can modify data in the device if it's not running. And we'll get back to some tricks with the bootloader later. The Windows Pocket PC software is constructed with a tool called Platform Builder. Because a Pocket PC is like I said, you don't have a hard disk or something, you don't put in a floppy, but you have a flash image, and the flash image has to be put in the device, but first it has to be constructed from all the tools you want to put in it. So if you think back to the desktop where your Windows system directory and your Windows directory that's copied from the CD-ROM onto your device, and Microsoft somehow put together the CD-ROM. In this case, the Platform Builder builds a huge memory image for a flash device, and the upgrade program for your Pocket PC just flashes this whole blob of data into your device and then boots from that, and then it starts running. And Platform Builder allows you to configure what goes in, how big areas are, how big a file system should be, or stuff like that, custom parts that are in there. And it just, one of the things it does, for instance, is for the ROM part of the device, it would be silly to put an executable in ROM and then load it into RAM to actually run it. So what they found is that they can leave certain parts of an executable in the ROM. So they kind of pre-link it already in the ROM. So it's already fixed where the execution address will be, stuff like that. And just the data areas will be coming from the RAM area. So, and this is called execute in place. Okay, what it does is, well, it boots a file called nk.exe, which is the kernel. And like I said, it's similar to the desktop. You have called a thing called Pocket Word, or you've got Pocket this or that, and it's all like on the desktop, but it's not the same. A group that has done a lot of hacking on the XDA is called the XDA developers. And one of the things they did with the software on a Pocket PC is create a few tools to manipulate these images and the data in the Pocket PC that's pre-configured by the distributor. So one of the tools that they created is a reverse platform builder, as it were. So it takes a flash file and just rips it apart in all the separate components again. So you get a directory, or actually a directory structure with all the files that were present in the flash file. So you can individually examine them. They are not capable of running anymore except on the device that they were taken from. Because the addresses in these files have been pre-calculated, they are fixed for this device, and you can't just take them to another device and run them there. But still, it's very interesting because now you can take these single files that you can't copy off a device just by using a copy command or something like that. They're special files in the Pocket device and you can't get them off normally. And you can take them now and put them through your reverse tools like IDA and examine them. Another tool that it made is a reverse platform builder, as it were. It takes again the files, or like an imitation platform directory structure with all the files that were present. And one device, one program that we found is tt command debug program. And what you see in the window is all the data that's been passed forward and backward with the GSM device as the thing is running. So this is a very interesting tool to understand how the parts are communicating. And actually what you see is that often the most stuff you find out about a device is through the debug and diagnostic tools that people leave on that device. Another component in the software that's very different from normal Pocket PC is called the radio interface layer. And actually this is the added component to the Pocket PC for the phone edition. Together with some more application level software, this is driver level software that talks to the GSM device. Basically it's an API defined by Microsoft, and actually it was closed. So they didn't want anyone to know for some reason. But we later found that they put a patent application for it, and in that application was the whole description of the API library. So that way we had full access to what it was about anyway. What we found is that it mainly is implementing the whole AT command set in an API. So instead of giving AT commands to the phone part yourself, you have to go through an API. And actually this layer is below another layer that's normally in Windows for telephony, which is called TAPI, T-A-P-I, the telephone API, which is also on your desktop. And this layer is below that and actually talks to the phone. Why is the RIL interesting? Because if you want to research security aspects of your phone, the most interesting ones are the remote ones. And of course, one remote entry to this device is over GSM. So if you want to research the security aspects of this device through attacks over SMS or whatever, you want to know what this layer is doing with the input it's getting from the GSM device. And actually this layer is just reading AT plus and then the whole SMS message that's coming in, for instance. And we've seen that they are fond of things like struct copy in this code. So you can imagine that there must be some problems in here with risk of overflows, for instance. Again, the risk is even greater because this is unclear who developed this code actually. It's not clear if this is really Microsoft code. Probably it is, but there are also maybe HCC involved in coding this, or the operators. And on the other hand, you have the VSM device, which has been coded by someone else. So that interface, there must be going things wrong there. Okay, again, a simple picture to see how things are connected in the device. So, like I said, you have the application, then you have the telephone API, actually then a middle layer called the service provider layer, and then RIL is actually talking to the hardware. Well, this is another picture that's not so relevant, but basically the RIL is a asynchronous interface. So it only works by you registering a callback and sending messages without waiting for the answer. And then when the answer comes back, you will get a callback with a notification about what happened. We also wrote a tool which, because there was no information on RIL at all, this is an example application that's using the RIL interface to give you notifications if SMS messages come in. So in the window you see what the information is that you get when an SMS message arrives. What actually happens is that this notification is going to the Pocket PC OS also, and there are all kinds of handlers taking care of an SMS message and making sure that if it's like a text message, it goes into the Pocket Outlook application, and then it's mishandled there. That's Microsoft. Anyway, this gives you understanding on how the RIL layer works. Okay, so now we've seen the hardware, we've seen the software. Now we can discuss some security aspects of this device. I have to say, most of it is a mix of really high-level stuff and possibilities and some more concrete stuff. So. The first thing that's always good to know is to make it clear what you could do with these devices and what the risks are without actually going through the whole motions of actually doing it. But just realizing that it could be done probably is enough for a lot of people to actually start thinking about protecting themselves. If you know that buffer overflows are everywhere and you have this device and the CEO has such a device, it's turned off, it looks like, but the phone is not. So you turn off your Pocket PC, but the phone is still running. And what happens is, if an SMS or an MMS comes in, the notification goes to the Pocket PC and it will actually turn on and start processing this message. So you put your Pocket PC on the desk, an SMS comes in, and if there's an overflow exploit that it's using, it could start running code at that moment in your Pocket PC. Okay, let's say we have a payload that turns on GPRS, because there's no need for user confirmation to turn on GPRS, so any software can turn on GPRS even if you turn it off. It will connect to the network, to the internet, and it can retrieve whatever payload or software it wants from the internet to start using that. So let's say we download our software that's doing voice over IP or whatever to record whatever is recording or being spoken in the room where the device is lying, and sending it off over the internet to whoever wants to listen to it. So instantly your Pocket PC is turned into this remote bug device without any user intervention. So basically the only thing that's missing here yet is the SMS overflow, because all the other parts are easily done. That's not a problem. Another thing is for corporate use. Okay, you get all these, I don't know if you have any experience with companies getting rid of modems, because people had these modems and they were using them in their PC and they were backdoors into the corporate network, because we have this big firewall and now people are using modems, so we get rid of all the modems. So now these days most PCs don't have modems anymore, so, or at least we can buy them without, and we can control that problem a little bit. And now we start putting these active sync devices into our corporate network, where, again, if the device, for instance, is infected with some software, we can just wait till we get active sync into a corporate network and use the GPRS to create a backdoor. Because this is actually the modem with GPRS, with Bluetooth, with Wi-Fi maybe even. And it's almost getting to be this uncontrollable backdoor into your network. So, with those ideas in mind, you can again look at, okay, how did Microsoft try to protect us, or how does the manufacturers of these devices try to protect us from abuse like this? If you look at that, we have to say that for the moment there's no protection at all almost against attacks like this. It's very feasible because there's no limitation to what an application can do in a device, at least for the pocket PCs. The smartphone is a bit of a different story. Although there are all kinds of measures that make it possible, either it becomes unusable by using them, or they are not used in default anyway, and by corporations at all, like we know it now. Okay, and if you look at the use of these devices, of course, again, the risk is getting bigger instead of smaller, because we're going to use it for multiplayer games, for all kinds of stuff, and at the same time, it's our business calendar and our business data that's on there. Okay, if we look a little bit at the security features that are put in. First one is the simple PIN code or passphrase on boot. So it boots up and you can't access the device, you have to know the PIN code. So this is a protection layer put in by Microsoft in the Pocket PC. Another thing is a so-called admin policy. And this is a kind of interesting feature because it really restricts the device quite well under certain conditions. What it does is it is a flag somewhere for the shell that's running on the Pocket PC, and the shell is basically the environment that controls anything that's to do with the Explorer, access to files, active sync, and it can set access controls on all those files. So it prevents you from downloading files to Internet Explorer, it prevents you from putting files through the active sync on the device, and it covers quite a lot of access points to the device if it's turned on. And the prerequisite is that you don't have an application on there already that allows you to do things without going through the shell. So if I put a command.x on there, I can just still copy files or modify files, even though the policy says no, because I'm not going through the shell. So in that sense, it's a bit limited. There are hooks for virus checking and stuff like that, so they have to put hooks for third party, and that's the generic thing. There are all kinds of things for third-party add-ons, but they don't put it in standard. So there's code signing, but they either don't use it, or it's used in such a form that you can't use the device almost anymore, because nothing is allowed. Also encryption. No data is encrypted on your Pocket PC default. So what are problems? All applications in the Pocket PC run at administrator level, or rather there's hardly a distinction between any other level than administrator level that we know from desktop. So you can read all the memory, you can write all the memory, you can read and write all the processes that are running. There's no access control whatever. So as soon as one bit is running on there, it has control over the device. So basically, you don't want to have any code that you don't trust running on it because it can do anything. The second one is something that's no longer true in the most recent versions, but this was a trick that they put in for the first versions because the GSM was so buggy. And what they did is, normally with a SIM card you have to enter your PIN. But if the GSM part is buggy and it's turning on and off all the time, you have to re-enter your PIN every time that happens. Well, of course, that's a pain. So let's put the PIN in the registry, and we'll just answer the PIN anytime the GSM part crashes. So they just put the pin readable in the registry the first time. Well, like I said, the non-executable protection, the admin policy, you can circumvent that with custom applications. The startup pin of password depends on 2 bits in RAM. And as I told you before, the bootloader has access to that. So, yeah, where is your security? It's gone, because the bootloader will give you access to the memory. You can just flip the 2 bits. You go back to the Pocket OS, and you're in. Like I said, the address does not need confirmation. All the data is encrypted, so if you get access to the bootloader, you don't need to know the PIN anyway, and you can read all the data from the device and process it later. Active sync. There's, of course, the PIN code that you can put on the device, and if you active sync, the PC will ask you for the PIN code. But the other way around is there's no authentication for the PC to know what the device is talking to. There is some kind of bonding going on, but that's quite limited. And you can just put in an empty Pocket PC and then synchronize all the PC to it if you want to. So it's an easy way to just read all PC data. One of the things that came up in the first version is, well, they sell it cheap with subscription and expensive without, and they use unlocking. And what we found is that when researching the GSM ROM that we got through some upgrades, and later we found through the upgrades how the mechanism worked, we could read the GSM ROM through the AT command set. We found that the memory location containing the unlock key was readable by an AT command. So you could just give the 80% read register command, and it would just give you the unlock code of your own device. So again, there was no security at all in this area. Actually, with the new device, this greatly improved. They put in all kinds of measures to prevent this. The only problem is that they put in another command that I'll get to later that lets you read the whole GSM ROM now, even without an upgrade or whatever. So currently we have read the whole ROM and understand the whole crypto algorithm that they're using now. Okay, insecure bootloader problem. Actually, I have a couple of slides, but I'm going to try and show this with the PDA here and the camera. So if you can assist me, I hope that works, because we tried it and it wasn't very clear. So if it doesn't work, we'll just go back to the slides and we'll do it from there. Yes, GSM okay. If I press the action button, it goes into a diagnostic mode. So what you can see here is all kinds of tests that you can perform on the device. Oops. Oh, this is the memory test. It's okay. I think there's a playback test. Actually, this is quite interesting because of all the tests. If you load this in a disassembler, you can really accurately see what all the hardware addresses are and stuff like that, because they are being used by these tests. So that's quite clear. Okay, so one of the tricks that we found is there's a special kind of SD card that you can use, because so another menu that they have is called the flash tools. So what you see here is you can write the ROM or the CD to an SD card, and well, that's easy to do backup, or if you want to examine the ROM. Well, what we did is we found that if you have a special type of card, and I now plug in an SD card in the bottom, I put again. That now it says that it now says that it detected a diagnostic card, and what you see is our Wallaby patch tool that's now running, because what it's doing is actually running code from the SD card now. So what we did is create a tool, and you see a menu here now that we created on the SD card. And one of the things that you can do now is, for instance, write a RAM to the SD instead of the ROM, or in password menu. And now the stupid thing I did was that there was no password just now when you saw it booting. I can activate it now again. So now I set it to bits basically in the PDA. And if I boot again, so this is our version again. So what it will do now is the password is activated, so if everything goes well, it will ask you for a password instead of, so now it's asking me for the pin code instead of letting me through. So I can't do anything with the device, so this is the normal mode. If I boot into the boot mode again, so the diagnostic part, so let's see, the password menu, so, no. Whoa! I almost destroyed my card. This is an old PDA also. So now I want to do is, okay, just want to go down. I do deactivate again, and it says, okay, I found the flag in the heap, and it's deactivated, and then I boot again. Everything goes well. Won't ask for a password. So it's really handy if someone leaves his device on the desk and you just want to peek into it, but you don't want to let him know that you modified it. So now I have access to the PDA again. And I can turn it back on again so someone won't know that I've been reading his pocket email. Anyway, so this is the trick that you can do with an insecure bootloader. Okay, go back to the presentation again. So actually, this counted on two things, namely the fact that it had this special mode in the bootloader that would allow you to execute code from the SD card. But of course, it's not always necessary to go through all these modes. As long as you can write 2 bits into the memory, then this trick will work. Okay. So this was a slide that pretty much described the same process that I was showing just now. Some tools that you can use. If you're going to look at development for a Pocket PC, then of course the first step is Microsoft with all its tools. And actually for the Pocket PC, they allow you a lot of tools for free. So the whole embedded C compiler environment is downloaded for free. It has a remote debugger. It has an emulator that runs in Intel that actually does the whole device. They don't actually, I'm not completely sure if they have one that also contains the phone part. And I thought they did, where you can use an AT modem to play the GSM phone. Platform builder, that's not free, that can create the images. And actually they've started a shared source program where they give parts of the source code for the Windows CE environment for free on the website. And that can also be helpful if you're researching. It's not really complete and they miss some essential components. But still it helped a bit in, for instance, looking for the place where they put the bits for the password. ARM is the main processor in all these devices, and ARM code is a pretty simple, actually, pretty simple assembly language. Fairly straightforward, RISC instruction set, which makes it quite easy to read and understand assembly code itself without going through decompilation or stuff like that, although I think in the future that will also be necessary for this kind of reversing. IDA Pro is a tool that I use the most for this. It's a very well-known disassembler with a lot of reversing options and recognition possibilities for function calls and stuff like that. And DLL signatures for the Pocket PC DLLs are also available, which also helps understanding Pocket PC DLLs and applications. Also, Linux was ported to the iPad, and that also gives you a lot of information on how the devices work and how the ASICs in those devices have been used. Because when HP had the iPad packs made, they made sure that they control the spec for this. And they've been using that internal information in assisting the Linux porting effort a lot. Unfortunately, they don't match that much anymore with the current HTC devices. But still, it's useful to have the tool change, the GCC ARM compilers and stuff like that to use readily. Okay, so what I said at the start is the XDA developers. So this is a group that did a lot of research on this device. And like I said, the reverse tools, the tools to break it apart, they're available from their website. Basically, it's a good resource to see how such a device is constructed, what you can find about a device, and how you can go about it. One tool that they created is called the XDA manipulator. It was the first and I think only unlock tool also for the XDA, but it also allows you to do more. It's based on the research of the GSM ROM, and it allows you to set, for instance, also other parameters. So not only the logs, but also the EMI, which was also easily changeable, other information, the call timers, stuff like that. So, like I said, 2 weeks ago I got a new XDA, the XDA2, and of course I was very interested in, okay, what did they change, what did they improve, and did they change anything? If you look at the bootloader, there was clearly a change. We also got access to a pre-release device, so we know what changes were made in the final one, and it was very clear that they removed quite a few commands from the bootloader. For instance, there's almost no diagnostics anymore in the bootloader. There's only one stress command to test the RAM functioning, but there's not the whole menu that I showed with all the sounds and stuff like that. If you go into bootloader, it means a hard reset of the device. And that's also very interesting, because that means that you can't go into bootloader, fiddle around with things, and then go back, because then the whole Pocket PC will do a hard reset, which means you lose all your data, and it will go to a complete factory reset. So that removes quite a few options. The only question, of course, is if you can prevent the hard reset from the bootloader. Because if you can prevent the hard reset by just, again, toggling a bit, then there's still the opportunity to just go back into the Pocket PC. But that's still under research. One of the things that we found is that they still have commands to read and write the whole memory space. So if you go into bootloader, you can still read and still write memory space. But actually they also changed the GSM bootloader. So because the GSM part is a separate part, it also needs a bootloader. In the XDA1 there was not really a visibility of this bootloader because there was no direct communication. Now there is. So you can configure the bootloader of the CE part to start talking to the bootloader of the GSM part. And that's interesting because they replicated all the commands, or a set of the commands from the normal bootloader in the GSM part, including a command to read the whole memory space and a command to flash part of the memory space. And this of course used for upgrading the GSM ROM. But it was also very interesting to see what was in the GSM ROM, of course, because they changed the security around the locking. And unfortunately for the people that wanted to lock the device, of course, that if you are able to read the whole memory space, then the only thing that will work is if you use some kind of public key crypto to protect against that. Well, they didn't, so basically with the ability to read the whole GSM ROM, you can almost immediately unlock the device again. If you look at the Pocket PC 2003 again, well, it's still running with the full admin access. The admin policy somehow doesn't seem to work anymore, but that can be just a bug, a versioning issue, because all the hooks are still there, so maybe it's a bug. It's still an encrypted file system, so that is something that I think is still one of the big weaknesses, and if you have such a device, I think it should always have some protection like the password, and it should always have something like an encrypted file system. Okay, now a complete switch again, because when I was doing research for this talk, I also went back to looking at what was happening on the Nokia front currently. And actually this is there are some quite interesting developments in that area also. The 6210 that I showed at the beginning is a phone from a generation called the DCT3. And Nokia makes their phones in a zillion models, but all the models are from a certain generation. And these generations have some common ground. And that's basically all the main code that's used for functioning in the device is common, and they just add features for different models. Now, the DCT3 allowed full flashing of the device. It means with a special parallel cable and a connector to your phone, you could write a new version of the software from Nokia in it. But you could actually write anything you wanted into it. They used a process which, again, we will see the bootloader come back. In this case, the Nokia phone has a bootloader ROM, so it's not in flash, but it's in a fixed ROM. And that's, of course, always handy, because a flash you can destroy, and then the ROM will always boot it again for you. In this case, when you press the power button, when a pin on the connector is pulled low, it will go into this bootloader mode. And what it allows you to do is, through a serial protocol, 2-pin protocol, it will allow you to send data into the phone. And in this case, it's a piece of code that it will run next. So this will be loaded at address, I don't know, 0, I think. And it will start running this code. And Nokia's distributed this code as part of their own upgrade process. And after this first, or actually second boot stage bootloader is running, this simple bootloader will load a second piece of code. And the second piece of code is actually the flashing software that's being used. And it's a simple loop with a few commands like erase, read block, write block, stuff like that. And then you have software for the process after this, which actually writes the data into the phone to flash the new flash. So this is actually quite a nice process, because it gives you full access to the data in the phone. You have full access to the flash file, you can read it from the phone, and understand it. You can reverse it, you can put it in IDA Pro and examine it. And B, you can modify it and put it back in the phone. So it's a great experimenting platform for GSM technology. So what happened in the last few months is that there have been a few developments that are very interesting. At least that's what I think. The first one is that there's a group now developing their own OS to put in your Nokia phone. So they actually reversed everything from the keypad, the LEDs, the display, anything in the device, also the serial. So they're actually now working on a serial port, so you have your data cable and you can talk to that phone over the data cable, maybe even have a shell on it. And all based on reverse engineering the normal flash file and creating their own flash file. Another part is that in the Nokia phone, there's default debug tracing. It's been used by Nokia for probably for internal debugging, for examining the device and repairing it. Some of you may know the network monitor mode that's in Nokia that you can turn on, where you can see all kinds of information on your cell that you're currently in and stuff like that. So that's also related to this. And what someone did is reverse this whole tracing protocol, and it now actually allows you to read all the GSM messages on the network through your phone. It will write them to disk, and they wrote a parser, and you can just see all the GSM messages according to the specification, fully specified, and you can just see what happens on the GSM network when your phone talks to it. So it's very interesting to learn how GSM works. And the last thing that's a little bit older is someone created a full ARM emulator that's able to run a flash file from a Nokia phone. Again, this is very interesting for the reversing process. So imagine we have the GSM ROM now also from this phone, and we just run it in an emulator, and we can see how it starts reading and writing from certain addresses. And you can, figure out as you go along how it interprets certain parts of the memory space. You can coach it along by just pushing some values in certain areas to get the code to keep it on running. And actually for the Nokia, you get a display of the phone on your PC, and with actually LCD display. And it runs all the way up to SIM insert. So they actually got it running. So this is, I think, a very interesting development that shows you what you can do once you put time in reversing closed and embedded devices. If you look at what Nokia did surrounding the possibilities of flashing, that's also interesting to learn from. Because the new generation is DCT4, and it's not so easy to flash phones anymore as it was with the DCT3 series. Already in the DCT3 there was security built in to protect you from writing a new EMI in there or changing your logs and stuff like that. In the case of DCT4, Nokia actually started using public crypto to protect their flash files. So they started by using encrypted bootloaders. So there's a key somewhere in the device that is able to decrypt it. But you can't create your own bootloader because you don't know the key. Flash files are signed, so you can modify the code in there easily. And now there are slowly developments that are, getting more light into how this works. But it's possible to create a system that's pretty closed, and it allows you quite a few fewer things that were possible in the past. And I think this is the type of protection that you will need from bootloaders to actually protect your device from abuse. And although it looks like the XDA2 is improved a bit, it still lacks the understanding that Nokia apparently did have when they developed this generation. This is a bit of a sidestep, but a lot of this information that you saw was discovered actually in the process of developing a secure phone solution. My partner, I run a company in pen testing, but my partner also has a company doing software development. And what they did is that they developed a software package that runs in the PDA and creates an encrypted GSM phone. Now you may say that the GSM is encrypted anyway, so why would you do it? But maybe you haven't followed the GSM world, but that crypto is so weak that it does cost about $100K now to buy a system that can listen into any GSM call at once as a man-in-the-middle attack system. So tapping of GSM phones from the air is actually already possible for people. Of course, within the telephone network, it's also possible to tap GSM lines. What this does, it actually creates a full crypto application that is untappable. And it all fits within the PGA GSM phone. And of course, during the development of this product, a lot of the research, like the ROM tools, were discovered and developed. Actually, there's also a Windows version for your desktop available that can do this over landlines, so it's not GSM only. But I thought I'd mention it because it's a nice result of all this research. So if we look at what we've seen so far and what you have in devices, I think there's still quite a wish list that you would want to have in a PDA that you really want to trust with your data. Because in the future we won't be running around with 3 PDAs. We will only be having 1 PDA, and that will be used for your games, for your entertainment, for your business use. So to get a secure device, we really need to start paying more attention to some areas, I think. Well, first of all, of course, the bootloader has been mentioned enough times, but also the encrypting of data would solve a lot of problems. If I can go in the bootloader and change something and go back, and the device doesn't even notice that something changed, you want to have something like that. But also things like really wiping data. If I delete my entry in a Nokia phone, it's still there in a flash file. I can read a flash file from a Nokia phone, and I can see if it had a BOP, like the browsing thing. All the cache is in the flash. So you can see so much data that's not wiped from the device when you say, I want to delete it. But also more user control. I want to say if I allow uninitiated GPRS connection, yes or no. I want to be able to choose if that should be allowed or not. Currently there's too little control over functions. It's either everything or nothing. Okay, so what can we expect in the future? I think hardware access, like I've shown, will improve also the software hacking, and it will become more and more necessary because devices will become more and more closed. But also the tools to do it will become more and more accessible to hobbyists and people without access to very expensive equipment. So, of course, you'll see that the problems of the desktop will move to the PDA. I mean, everything you've seen on the desktop you can expect on the PDA, unless people solve things first, but I don't think so. For some reason, embedded devices give the impression of being very difficult to hack. And I think that's a problem in the perception. It's unjustified because actually, like I've shown with the unlocking of the device, sometimes it's so simple to hack the device, you wouldn't believe it if you hadn't seen it. It's just the fact that you just go in and look, and it's not the fact that it's very difficult or needs a lot of wizardry or mathematics to actually be able to do it. Finally, the whole development environment for embedded devices is getting more easy all the time. First of all, we're now putting Linux into every embedded device, so that also already helps because it's a known OS. But also the whole development process is being improved because people want embedded devices with all kinds of features. And that also helps attackers of devices, and it also increases very much the risk of bad applications. In the past, you had to be very careful in your coding for embedded devices because if you had to go back and do it again, it took a long time. Development cycles were long, so you made more sure that your application was doing the right thing. The easier the development process gets, the worse the software gets. That's generally what I find. Okay, so I'm getting to the end of the presentation. Some people that I think were responsible for quite a few things that I mentioned today. It was certainly not all my work. The XDA developers as a group. It's me as a coder of all the ROM extraction tools. And Peter van Spek is the guy who wrote the patch tool that I showed with the SD card. So quite a few people got involved in this. Well, this is almost unreadable, but on our website there is also a page with some background on this information. And you can also go to the XDA developer site, of course, where there's also a lot of background. And with that, I want to end and see if there are any questions. No questions? Okay, that was it. Thank you.